Hey, it's Stereo Police, back with yet another video of a piece of Yamaha equipment. In this case, we're looking at the R-9 natural sound stereo receiver. And I picked this one up a couple weeks ago for a pretty good price. I was intrigued because, well, for a couple of reasons. Number one, the Yamaha gear of the 80s, even of the 70s, but of the 80s was I found to be so good. And this particular receiver, it's not an integrated amplifier, it's a receiver, but I was intrigued because it was manufactured about 5 or so years after my A1000, which is an amp that I've made several videos about and I love so much. So it's a later manufactured receiver and a later design, and yet it has a lot of similarities with the A1000 in terms of this little drawer that opens up, the tone controls, and the various buttons inside the drawer have a similar feel and layout to the A1000. And this one also has an auto Class A button, as well as a tone bypass that I very much appreciate. And like the A1000, although in a different location, this amp has this variable loudness control that I never use. But Yamaha was known for that. Instead of just having a single push button loudness control, you can vary the influence of the loudness depending on your tastes. But I found that the variable loudness control in the A1000 is just ridiculous. It does too much too soon, and I didn't find it to be very effective. But I rarely, if ever, use loudness controls anyway, because I want my signal to go through the amplifier in its most pure form with a flat frequency response. And effectively, with a loudness control, you're vastly changing the frequency response of the amp. It boosts lows and it boosts highs, and I don't want that, so I don't use it. So I picked this receiver up not to use as a receiver, but I was intrigued about the integrated amplifier aspect of it, and to see whether it was as good or better or not as good as the A1000. I'm interested in the Auto Class A, of course. So as you can see, it's a receiver. I haven't plugged it in yet. I'm going to in a minute. And this is back in the 80s when video was creeping its way into receivers. So you see we have some video 1, video 2, and that sort of thing. There's some video down there, but I'm not the least bit interested in that. I'm interested in putting a signal into, for example, let's pick the CD, putting a signal into CD. I'm interested in bypassing the tone controls, and I'm interested in turning on Auto Class A and just using the volume knob. Now, right off the bat, everything's got a high quality, sort of a high quality feel to it. The faceplate is aluminum. The drawer cover is aluminum. The knobs down here feel like, I'm not sure if they're aluminum or plastic, but they have a knurled edge to them, and they feel high quality. The buttons, the feel of them is all, decent quality per Yamaha of the 80s. The volume control has a really awful feel to it. It's kind of tight, and it's a plastic knob, and it's got some weird thing. I don't know if you can see it inside of there, but as you turn it, I see wires moving. See those wires? They just kind of move. And I'm not sure I've ever seen wires moving along with a volume control. I don't know if something's loose back there. I'm not quite sure what's going on yet, but I'm going to find out. There's something rubbing. See that? I hear something in there. Anyway, so this is the front panel. Let me turn it over to look at the back panel. Again, I'm only interested really in using this as an integrated amplifier. Alright, so here's the back panel. It hasn't been cleaned. I haven't done a thing to it. What is that? I can't rightly tell you. I know what that thing is. Anyway, got some antenna hookups down here. There's our video ins and outs, and there's our RCA jacks for the tape and tape 1, tape 2 CD accessory. So that accessory there is going to output a signal from the I guess from the preamp, and then you can run it through something and then input it back into the amp. Something I don't use, so I'm not that well versed on it. The binding posts are plastic. They're all, I hate these ones that kind of wobble around. They're, this is standard issue of the 80s for regular consumer equipment, and you can pinch the wire down, stick the wire down in there and tighten it up, pinch it off, and it looks like these, nope, they don't. These do not receive bananas. And then there's our AC outlets. I would never use that. So that's the rear panel. And let's go over a couple of specs that I pulled on it real quick before I try to fire this up. Actually, you know what? I did print a few things out that I want to talk about before we kick this in, just about the design of it, and then I'm going to compare and contrast this. I'm really interested in contrasting this with the A1000 in terms of design as well as in terms of sound. I'm really hoping this thing sounds good, given that it's it's got that Yamaha Auto Class A, and I've already looked at the schematics and compared them. I've got a couple of things I want to cover here that I find interesting. Hope you do too. Let me pop this camera on a tripod. Alright, so get a pointer here. Now, what I have here is the specifications of the R-9 that we're looking at now versus the A1000 versus the AS1100. Both of these, of course, being amplifiers that I own and that I've recently covered in videos. And starting with the R-9, we can see that it's rated at 125 watts. Looks like a power bandwidth from 20 Hz to 20 kilohertz with 0.015 THD into 8 ohms. Let's use 8 ohms as a comparison here. The A1000, on the other hand, again, is rated at 120 watts. Looks like less THD, 0.005 into 8 ohms. And the A1000 gives us a Class A wattage. It says 10 watts in Class A before it switches over to Class AB. Unfortunately, the R-9 doesn't tell us how many watts we're going to get in Class A mode, but I'd like to find that out. And I have a way to do that once I get this hooked up to the test equipment. Okay, the AS1100 is into 8 ohms, rated at 90 watts. 90 watts. And that's 90 watts, 20 hertz to 20 kilohertz, 0.07% THD. Now, the only other really specs that I care about, dynamic headroom, not really. Oh yeah, I care about damping factor. I haven't talked about damping factor very much, but there are a lot of specifications that I don't pay too much attention to. THD is one of them. As long as it's below, 0.1%, it's just going to be almost irrelevant and imperceptible to the human ear, really. And so THD is not going to tell us a story, but damping factor right here does give us, as long as you have really good speaker cables, a low gauge, a fat wire that's a low resistance, and you don't have long runs, the damping factor can tell us a little bit about how your amplifier can can control the woofer in the speakers. How well it can control the motion of the cone, which is really important. Now, the higher the number, the better. The higher the damping factor, that means the lower the output impedance of the final amplifier stage. And so with our R-9, we have a damping factor of 60. With our A1000, we have a damping factor of 90, so we have a better damping factor in the A1000. And with the AS1100, we have a damping factor, that's hard to read, of 250 or more. That's an incredibly good damping factor on the AS1100. That might be one of the reasons that I've noted that the AS1100 is just so incredible with respect to bass, such control. And up until today, I've never even looked at the damping factor specs on the AS1100, but when I looked at it, I was like, wow, maybe that's one of the reasons why it's so damn good. So the R-9 has the lowest damping factor, but between 60 and 90, it's not too much of a difference. And those are really the things that are of interest right here. You know, input sensitivity, whatever, dynamic headroom. Dynamic headroom doesn't really come into play too much unless you're cranking up the receiver till it's damn near its maximum power capabilities. But with my Forte 3s, I hardly ever exceed 1 watt, and so it's got all the dynamic headroom one could ever ask for. Okay, now of note with the R-9, I pulled this out of the service manual. The idling current, and I've run these numbers right here based on the resistor. You adjust for a 10 millivolt voltage across the output emitter resistors, and the output emitter resistor is 0.22 ohms. So you get 46 milliamps of idling current in Class AB mode, and when the Class A is switched in, that 10 millivolts goes up to 60 millivolts, which results in 273 milliamps. So we get basically 6 times the idling current in Class A, and that just biases the transistor up a little higher to result in that Class A operation. Moves the quiescent point up the load line, so to speak. Now, I'm going to go over these same diagrams. These are from the service manuals. I'm going to start with the R-9. This is the R-9, and then I'm going to talk about the A1000 just to show you the differences. There were some design changes made over the course of the 5 or so years between the A1000 and the R-9. Again, the A1000 was made roughly in the early 80s, maybe 1980, 81. The R-9 was made roughly in the mid 80s, maybe 85, 86. So with the R-9, I'm just going to follow the circuit path, and this is the block diagram from the service manual, and I'll just pick CD. It could be tuner, it doesn't matter. And the first thing we hit is an integrated circuit, IC404, and all that integrated circuit is a switch. It's just a switching device. It's not an op amp. So we follow the switching device. It switches it in, and we follow it over to our send and receive accessory. That's that bus bar on the back I showed you. And then the first thing we hit here is our loudness control potentiometer, and I'm keeping that off. And then we go into the volume control, so the loudness control through the volume control, and then we go into what's called the tone amp, and I'll show you that on the schematic. And that is an integrated circuit, IC501A, and there it is from the service manual. It is an op amp. It's an operational amplifier, which I consider to be evil. Blasphemy. Heresy. Terrible. Op amps are disgusting. Should never ever find their way into the signal path of a high-end amplifier, ever, or any component. But there it is, and here's our tone bypass, and I can show you that, well, basically the tone bypass as well as the tone controls are in the feedback loop of the op amp. So even when you bypass the tone controls, the op amp is still functioning, the signal still goes into it, and it's functioning as a flat amplifier frequency response wise, but it's functioning as a gain stage. It's basically the gain, the voltage gain stage of the preamp. So you can never get rid of that thing. It's always going to be in the circuit. That bothers me. Okay, and then we come from the op amp, which comes from right here, and then we go into what's called a simulated stereo mode. I'm bypassing that. I'm not using that. I don't need to simulate stereo. Then we go into our balance potentiometer, and then finally into our power amplifier that has a Class A switch. This is Yamaha's zero distortion rule. I haven't studied that, but looking at the schematics, it looks like a fancy name for something that everyone does anyway. It looks like bullshit. But it's basically negative feedback. Okay, so we go through our power amplifier into our final relays and into our speakers. There's some protection circuitry that almost all these amps have, and it just monitors the output, looking for faults, shorts, and clicks on the relays and shuts everything down before you burn the house down. Okay, this for the R-9 is basically just because I couldn't, these are all cut from using a snipping tool from the service manual, but I just pieced together the tone amp with the filters that are going to be out here, and you can see that basically the tone bypass just either switches over to filters in the feedback, in the negative feedback path, or no filter, just a resistor for typical op amp design, typical tone control design. But you can't. The point being, you can never get rid of the op amp. It's going to be in there. And pulled directly from the schematic, here is that evil op amp right here, and there's our, I had to piece these two sides together, but here's our on-off switch for our bypass, and when it's on, basically the signal goes through the op amp, and the feedback loop is a resistor. There's a little bit of compensation here, but it's still going to be a flat frequency response with a gain. And when the tone bypass is off, the feedback loop passes through some filters and right on back, and you get filtration, which emphasize the lows, emphasize the highs, bass and treble, that kind of thing. And finally, here is a schematic of the power amplifier section, and it's a typical design. A lot of these power amplifiers, especially from the 70s, but even modern ones, they all start out, the signal comes in, they start out with a differential amplifier, and that differential amplifier provides a little bit of voltage gain, and it amplifies the difference between the negative and the positive. So any noise on the line will be canceled out, leaving only signal. We go through a little cascode stage here, provides a little voltage gain. I've got to look, this is kind of tiny. And then basically, well, what I want to note here is there's a little biasing going on right here. There's a bias adjust right there. It's so small I can't see it. But basically, the interesting part, there's drivers right here, and then the output transistors there's two of main outputs, and they are paralleled. They're not a beta multiplying Darlington pair. They're they're each. They're a complementary pair, so on one side we have NPNs, on the other side we have PNP, and there's two of them on each side, and they're in parallel. And I have expanded that right here so you can see. This is the for the NPN side of the complementary pair push-pull. Our signal comes in through a 2.2K. Boom, signal goes out. 2.2, signal goes out. They're just basically in parallel, and that provides doubles the current capability of just a single output transistor in the complementary pair. But this is fundamentally a different output complementary pair configuration than we find in the A1000. A very different design, and I expect it to sound different as a result. Now, for the A1000, following the signal path, I'll pick, doesn't matter, tuner, digital audio disc, auxiliary, doesn't matter, comes up, and we go into the input selector, and then we have muting, and then we have our volume control potentiometer right off the bat. We have a subsonic filter that can be switched out, and then we go into our op amp right there. Hopefully, I'm looking through the viewfinder, hopefully you can see that. Now, here's the op amp in the A1000 that you can never ever get rid of. Now, I can tell you that the AS1100 has no op amps whatsoever in the signal path unless you switch in the tone controls. And you'll hear a little relay click, and it uses op amps. But the beauty of the AS1100 is when you don't use the tone controls and they're flat, a relay completely bypasses the op amps totally, and it goes into a fully discrete gain stage. That might be another reason why the AS1100 is so incredible. But here's the op amp right here, and the tone, the filters for the bass and treble are in the feedback loop. And then here's our direct mode right here. It just signals. Well, I don't know what that's trying to signal, but there's a switch on either side, and that direct mode will again can the tone control filters in the feedback loop, but our signal is still coming through the op amp, and the op amp is used as a 14 dB gain stage. Hold on a second. Okay. So provides a little bit of voltage gain, and then we go from there. High filter, we can switch that out. Then we go to our balance control. Again, this is the A1000. And then we go to our main output amplifier with our Class A mode, and there's our protection circuitry and our output relays. And I'll make this quick, but these are the evil in the A1000. These are the evil op amps that, here's a signal path right here. These are the evil op amps that you can never get rid of, even in the direct mode. And the A1000 of note is, you can see from the schematic of the output amplifier is literally, it begins here, the main power amplifier, and it ends right there. It's quite a bit more complex than the R-9, but nevertheless, it all begins with a differential amplifier, and then a cascode, then a voltage gain stage, pre-driver. Here's our bias current, bias adjust, and this is a transistor that controls the bias based on heat. This transistor literally sits on top of the heatsink and varies the bias based on heat being generated at the heatsink and prevents thermal runaway. Prevents overheating. And then the output, though, is we've got 3 transistors that are common collector configuration, 1, 2, 3, arranged in a beta multiplying Darlington pair. So the emitter of one feeds the base of the other, the emitter of this feeds the base, the emitter comes down finally to our load. So we have complementary pairs, NPN, PNP. It's a push-pull arrangement, but there's no paralleling of transistors. So the current that the load sees is supplied, the final out current is supplied all by this transistor and that one right there. So no paralleling of the outputs. Okay, I've made some notes about some things I want to test on this and some things I want to do, but so there are some differences in design. So now it's time to see if the R-9 actually fires up and works. I'm confident it will. The person I bought it from I have no reason to doubt them. They said it works. They fired it up. It works. So I'm not going to go through any formalities here. I'm just going to plug the thing in, start it, turn it off. I'll go ahead and hook up a dummy load. Maybe I'll take a risk. Nah, I'll just do a dummy load and we'll take a look at the, well, right off the bat we'll take a look at we'll put a signal into it and take a look at the output across an oscilloscope, and then we'll do a peak power test and see if it's true that this amp can supply 125 watts. So stand by. Alright, so I've got the amp powered up. It's got a nice, there's a glare there, but it's a nice red, you know, it's not a LCD. I hate LCDs. It's a nice, what do you call that type of display? Vacuum fluorescent type display, very nice. Looks like all the lights are turn off auto class A. Have a CD input. All the lights appear to be, LEDs appear to be red. It's a very red. There's a light on the volume control. That's kind of nice, having that light on the volume control, so you can kind of, when it's dark, you can kind of see the volume level. So let's go to the back. I have the left and right speaker A hooked up to two dummy loads, left and the right dummy load. I'm looking at one channel, the right channel. I'm probing it with the oscilloscope. No signal yet, so we're going to be looking at the output waveform. And I have as input, I'm using my El Cheapo. I'm not using my good audio generator right there yet. I'll use that for THD measurements. But I'm using my El Cheapo. I really like this thing, my Coolertron signal function generator. And I'm inputting a sine wave at 1 kilohertz at 2 volts peak to peak, which is roughly 0.707 volts input. No offset, and that's being input to the CD input. So let's go ahead and turn up the volume just a little bit. Alright, so I'm going to rotate the volume knob. Okay, that's all the way off, all the way on, and you can see on our measurements right there, we have right now I have about, there's our frequency of 1 kilohertz and our RMS we have 1.5. You can see our RMS voltage will change when I rotate the volume knob. So far a good clean signal. I'll check the other on the other channel separately. We are currently in Class A mode is off. But we have a good clean signal. And what I want to do is, with our 1 kilohertz input tone, is I want to crank this thing up till we see some clipping. Those flat edges on the top and the bottom of the sine wave. And then very briefly, I say briefly because my power resistors can't handle that kind of power for too long. I've got a monster power resistor bed right here. I don't feel like hooking that up. But we can get the clipping, and then I'll quickly turn it down, and we'll get the RMS voltage, and then we'll calculate the amount of power being delivered through an 8 ohm load. Alright, so all I'm going to do is let me turn down the vertical here a little more. One more. Alright, let's crank her way up. There's clipping. Okay, I'm going to turn it down just for a second. Okay, now that I know I can visualize clipping on this setting, as soon as we start to see clipping, I want that RMS. Boom, right there, 34.9 volts. Let me set the camera down. And I've got a calculator here, so that's 34, what did I say, 0.9? I'll go with 0.9. Yeah, 35. So 35 volts It's V squared over R, so times 35 volts divided by 8 ohms. That's 153 watts into 8 ohms. So that exceeds Yamaha's stated spec of 125 watts. So this is a very powerful amplifier. I forgot what numbers I got when I was looking at the A1000, but it wasn't 153 volts. It was lower than that. I think it came in spot on at 120 or something like that. I forget. It's an older video. So far so good, and it didn't, nothing crapped out, nothing died, nothing zapped, none of that sort of thing. So let me try something right now, just a brief test of a brief indication of frequency response. I'm going to hit pause for a second. Okay, so right now, and this is one of the reasons I'm using this function generator, is I'm sweeping over the period of a time period of 1 second. I got 1.1, but it's roughly 1 second. I'm sweeping frequencies from 20 hertz to 20 kilohertz, and with that, we're looking at the output and just seeing if we see any attenuation on either end. And I see nothing. As you can see that the yellow waveform stays roughly at the same amplitude from 20 hertz to 20 kilohertz. And no problemo. No problem with frequency response. Let me see if I can increase the frequency range and see it start to taper off. Okay, so what I have now, as you can see, the end frequency is 90 kilohertz. So I'm sweeping from 20 kilohertz to 90 kilohertz, and here's what we get. You can see that as the frequencies go higher, there's the taper off. There is where our high frequencies start to taper off as we approach 90 kilohertz. But that's irrelevant. As long as I get a good flat response from 20 hertz to 20 kilohertz, that's all I really care about. I'm not so concerned what happens at 50, 60, 70 kilohertz. It doesn't matter. It's irrelevant. It's not, you can't hear it, and I'm not a believer in having. It's a different story, but I'm happy. We have our stated frequency response range, no problem. Okay. Let me see what else. I don't know what else I was going to do before we open this thing up. I'm looking forward to opening it up. I'm just looking at my notes here. Get a look at what's inside. Test for peak power. I can't. I do want to do a THD. Oh yeah, I want to do a square wave test. Thanks for reminding me. I never filmed square wave tests, but a square wave. When you put a square wave in, 1 kilohertz square wave, you should see a nice clean square wave out without any ringing on the square wave. It shouldn't be getting rounded off, that sort of thing. And I won't get into details, but a square wave can tell us quite a bit about what the amplifier is doing to a signal if it's doing anything horribly wrong to it. So I'll hit pause here and I'll get that set up. Alright, so I've got a 1 kilohertz square wave going in. Same thing, 0.707 volts peak. And here are the outputs. Now let me explain something. Okay, our yellow output is going to be what's across the dummy speaker load. It's a nice, it's a fairly clean square wave. There's no pre-emphasis, there's no rounding off, there's no ringing. And the blue square wave is the input wave. So that's what's being input. Not a great square wave, but that's what's being input to the amp. And let's put them both side by side, and I'd say all in all, it's a pretty good square wave response. If you're interested in knowing what to look for, what horrible square wave responses mean, you could type in square wave test or square wave response of a power amplifier, and there's plenty of information online. But there's nothing horribly wrong to speak of here, so that's a good sign. So far our amp is behaving rather well. No issues. I think I'd like to do a THD and then call it a day. Well, yeah, I'll call it a day on this video, and then we'll open it up. I can tell just from looking inside through the grill here that things are pretty dusty. the top of those filter capacitors, very dusty. So I don't think this thing has been opened in a long time or cleaned or serviced or worked on. But let me go ahead and get my THD rig set up here, and we'll finalize things with that. There's nothing I can do with respect to. And by the way, I'm doing all this. You know what? I should have done this before, but let me click. I don't think it's going to make a difference, but I'll turn on Auto Class A. It's on. It's off. It's on. You know, no difference. Let's do that with a sine wave. Let's see what happens with a sine wave. You're not going to notice a difference. But, okay, there's our sine wave. Again, the yellow is the output. The blue is what's being input. You know, right on top of each other. There's, you know, I mean, there's no visible distortion. Not that, you know, when you're down into that less than 0.1% range, you're not going to see it. Yeah, but okay, Class A, on, off. Okay, on. Let's just look. Forget the input. Let's just look at the yellow wave, which is the output. Okay, Class A is on. Off, on, off. You can't see any difference really. I believe the difference is maybe audible for various reasons, but you really can't see the difference by looking at the sine wave, because both in the Class A mode and the Class AB mode, the distortion is exceedingly low. So low that you're not going to see any difference in the actual sine wave. So, okay, I'm going to need to change my rig around here a little bit and hook up the Keithley, which is the THD meter, and then I need a nice low distortion input signal from my audio generator right there. I'll be back in a spell. Alright, so I've got a 1 kilohertz, roughly 1K. Signal coming out of my audio generator. We're looking at it right here. You can see it's 712 millivolts. So less than 1 volt RMS, but approaching it. And I have right now I've got the Keithley THD meter hooked directly to the input, so we can see what kind of THD that our signal generator is gracing us with, and it's pretty damn low. It's 0.005%. That's why I love this thing. I love this this audio generator. So, and we are at 1K. Let's look again. We are at 1.015K, and the receiver is on, and the volume is down. So now I'd like to switch over to the yellow channel. Okay, blue is our input, and okay, and so there's our output. So I've matched our output level to our input, not that that matters. And actually I like to measure THD at roughly 1 watt output. So 1 watt is across an 8 ohm load is a RMS voltage of 2.8 some volts. So let's go ahead and achieve, looking at our yellow here, let's go ahead and achieve about 2 point. Okay, just lower this a little bit. Okay, let me turn off our input so we can just look at our output. So we're just looking at channel 1. And that's too high. We want about 2. Okay, there's 3. It's about 3 volts. 2.933. So roughly 1 watt. 2.6, 2.7. Okay, roughly 1 watt. Now I need to switch the Keithley over to look directly at directly across the speaker load, so I'm going to hit pause to do that. I can't do it with one hand. Okay, so now I have the Keithley THD meter hooked up directly across the speaker load, 8 ohms. And using the Keithley, now I can use it as a frequency counter or a voltmeter. I'm using as a voltmeter now. We have roughly 2.67 volts. We're close to being 1 watt through an 8 ohm load. We've got our frequency roughly 1K, 1 kilohertz. And then let's do our THD, and it is 0.238. So it's significantly higher than the spec, and I'm only at 1 watt. So that's 0.23. That's significantly higher than I expected it to be. I would have expected 0.01, 0.02, maybe 0.05. So 0.2 is surprising, and we're only pushing 1 watt now. Just to make sure the Keithley's doing its job, let's do two things. Let's start to turn the volume down, and when I turn the volume down, okay, let's see how much voltage we have. We've reduced the voltage to 1.7. See, like something happened. Oh, by the way, I'm not in auto class A. I'm just in class AB. So at 1.7 volts, you know, our THD suddenly went down to a respectable number. Now let's turn the voltage back up to roughly 3, you know, where THD started to rise. And see, we're back to 0.2. So something between 1 and 3 volts, just all of a sudden the THD just starts to, something happened. It just starts to rise to a level that I didn't expect. And just for shits, let's go ahead and figure out where clipping happens. Let me feel my resistors and make sure they're not going to crap out on me. Okay, where's clipping going to happen? Okay, there's clipping. Okay, watch this. I'm gonna turn it up, and I'll tell you when it clips. I'm looking at the scope right now. Boom, clipping. There it is, 11%, right? Look at that. Okay, let me turn it down to where it's not clipping. We're down to 0.1. So at high power levels, it's only 0.1. Now let's go back down to that. So the distortion actually went down as the power got to near peak. Let's get back down to our, there we're at 3 volts. And we're back to 0.2. And that's kind of a typical power curve, okay? If you look at a typical power versus distortion curve of an amplifier. Okay, all of these percent THD versus power. You do see it go down, down, down right before clipping, and then it goes up like that. And that's kind of what we just saw. So somewhere at low levels, like 1 watt, we were at 0.2%, and then it went down to 0.1%, and then, you know, of course at clipping it goes up to 13%, plus. All right, now let's see if there's any difference. Let's go ahead and go to our voltage and get back to 1 watt. So which is 2.83 volts. We'll just go somewhere close to 3. It really doesn't matter. Okay, 2.9 volts. Okay, we're still at 1K. Let's do some THD. And we're back to our 0.26. Isn't this Keithley awesome? I love this thing. And let's go ahead and switch on Auto Class A. Okay, all things are the same. I'm going to tell you when I'm going to switch it on and see if there's any change in THD. Okay, ready? Auto Class A is now off, and it's about to go on. On. Nothing. Okay, off. Off. Nothing. Nada. So while Class A is, you know, I love Class A operation just because it's more of a pure form of amplification. In this case, and in most cases, it's not going to make a noticeable difference in THD. Because, well, I'll get into that later. So, but, okay, there you have it. So the THD is respectable. By the way, let's say, you know what, since I'm hovering around a watt, and I listen to music at around a watt because of my speakers, my Forte 3.0 efficient, but most people might be pushing 10 watts or so on a lesser efficient speaker. So let's go ahead and put in a signal to simulate 10 watts, and then let's look at the THD with that. Okay, so there's our output signal, and I've adjusted the volume knob to achieve 9 volts RMS across the speaker load, and 9 times 9 is 81, divided by 8 is roughly 10 watts. So 10 watts, let's see what our THD is. 0.26, so it didn't really start to go down at 10 watts. It's roughly the same as where it was. Let me crank up the voltage and see where it starts to go down. There it is. It started to go down right there, and we are at 21 volts. So at 21 volts RMS, I'm just running some numbers here, we're at 55 watts. So it starts to go down at 55 watts, but again, we're you know, I don't know, it's still respectable, but it's higher than I thought for this receiver. So, all right, I've done enough. I think it works. I'm going to repeat this for the other channel. I think right now we've been looking at the right channel. I'm going to repeat it for the left channel. Oh yeah, you know what? I can tell you I've done most of this testing in just Class A/B. I haven't done Auto Class A, but let me go ahead and turn on Auto Class A right now, and let's output a few watts. Hold on, get like 5 volts, couple watts, and let me see if this thing starts to heat up. Right now it feels, you know, it's in Auto Class A right now. It feels fairly, I mean, it's warm, but it's not anything like the A1000. The A1000 gets hot as heck. In fact, it gets hot as heck idling. Let's just let it idle in Auto Class A. How's that? Turn the volume down, let it idle, and let's see if it starts to get significantly hotter. I'm gonna hit pause, and I'm gonna feel it. I can tell you the A1000, when you turn it on, it's hot within about 2 or 3 minutes. So I'm going to hit pause and wait 2 or 3 minutes, and I'll let you know if I can feel the heat coming off this thing. Well, it is getting hotter. It's getting warmer, there's no doubt about it, but it's not nearly as warm as I feel in that A1000, but it is definitely getting warmer, especially back here. Interestingly, you can see the heat sink right there. It runs from there all the way to the back. The back part of the heat sink is getting warm. The front part, almost cool. So it looks like the heat's coming from back here. And yet the transistors, you probably can't see, they run the whole length of the heat sink. I wonder what that means. It may just mean that this thing is on a tilt, and maybe the heat's rising and coming out the back. I don't know, but to me the heat ought to be uniform. Okay. It's not getting nearly as hot as the A1000 though, but okay. It'll be interesting to figure out when I open the panel, when I open the cover and get in there. We're going to do a test to figure out how much Class A power this thing can deliver, because we know the A1000, and I've confirmed it via testing, will put out a good 10 watts Class A. I wonder what this will do. I suspect it's a lot. I suspect it's less. I don't know why. Yeah, it's starting to heat up pretty good. But I don't know. I have no reason to believe that. But anyway, okay, I'm going to turn this thing off, turn the equipment off, and call it a day for this particular video. Hope you enjoyed it. and we'll go from here. We'll go to part 2 and pull the cover and take a look at the innards and do some more tests, have some fun, and then ultimately hook it up to the speakers and see how it sounds and how it compares to the A1000 as well as the AS1100. It's up against some big boys there. It's up against some awesome amps, so I have no idea what to expect, but it'll be fun. Ciao. Thanks for watching.